All right, so last lecture we talked about kinetic and potential energy. This lecture we're actually going to talk about restoring forces and elastic potential energy and like spring potential energy. So we have one form of kinetic energy dealing with motion. Now we have two different forms of potential energy, one dealing with position, and then the other one dealing with the conditions within a spring. So the way we're going to talk about restoring forces is actually with Hooke's law, and we're going to talk about where that came from and how that's derived. So Hooke's law is essentially the force produced by a spring when it's either stretched or compressed. And we'll also talk about that stored potential energy as well. Okay. So generally, restoring forces, a restoring force is essentially a force that brings a system to an equilibrium, position. Okay, so that's a force that restores a system to its happy place, so to speak, like where the system wants to be. Okay, so any force that does this and brings a system back to where it wants to be is essentially called a restoring force. Systems that have this property where they demonstrate a restoring force, those are called elastic systems. So definitely springs are an example because you can displace them and they kind of naturally want to go back to their equilibrium position. So let's think about the spring here on the right. So suppose this spring that naturally sets at this particular length, SE, okay, that's its equilibrium position. I'll jump over here and mark that. So you can see in the top picture of the spring, it's naturally wanting to set in its equilibrium position, which is SE, okay? And of course that is unstretched because it's equilibrium. If we stretch the spring to some positive length, okay? So notice our, there we go. Oops. So notice we have, oh goodness, my slides are acting up. Okay, so notice we have, we're moving it to the right. Okay, we have our generic x-axis here, or sorry, s-axis. Okay, so we're going to move the spring, we're going to displace it. So remember, displacement is final minus initial. So our displacement is going to be positive because it's going to wind up, the spring will wind up longer at the end than what it was when it started. So a greater final minus initial. Okay, so we're going to stretch the spring to some positive length. Okay, I've drawn that here in the second frame. You can see it here in the blue. We're stretching to some positive length. Okay, well that means that the spring is going to, it wants to pull back. If you've ever stretched the spring, you'll know that it wants to pull back to equilibrium, okay? And you can see that here with the red force vector, okay? So it's wanting to move back to the left even though we're pulling it to the right. And then same thing, if you compress the string, okay, so you're going to push the end of the spring in the negative direction position-wise, right? And we've got that here. Okay, so if we want to compress the string, it will push back in the positive direction, as you can see here, because it wants to return to that equilibrium. It wants to return to SE. And that's true for both situations here. So that's the idea of a restoring force. Essentially, if you perturb it or push it a little bit, it's always going to supply a force to try and get back to its happy place. Okay, now let's think about another example here. So let's say we hang a massless spring vertically such that its equilibrium position is L0 or L0, as the old physicists used to say. Okay, so I'll mark that here in green. So there's our spring hanging vertically. It's massless. We don't have to worry about its particular mass. And there's our position, it's L naught, okay? Now, if we attach a mass to it, like shown over here in this next image, if we attach a mass to it, well, that's going to stretch the spring, it's going to bounce a little bit, but if we leave it alone for a while, it's going to reach a new equilibrium position where it's not accelerating anymore, it's just sitting and happy, okay? Well, if we do that, it's going to reach this new length because it's a new equilibrium position, okay? So the string will stretch downward, the system will reach a new equilibrium position at L. Well, I can label that here, okay? So in orange, I've labeled this new stretch length. Okay, well that means there's a displacement has happened, right? So our final minus initial, there's definitely a change in L. So our final is length L minus our initial length, which was its equilibrium length, L naught. Okay. Well, this means that the weight of the mass is causing the spring to resist with an equal and opposite force, right? The spring's not bouncing up and down anymore. We waited for it to come to rest. It's not in its equilibrium position, so we know there's a force actively acting on it, okay? So because its position, so we'll say because y does not equal L0, there is a force. And we know that force is the mass of the block or the object that we hang on this spring, okay? So let's set up Newton's second law situation here. Actually, it's going to be Newton's first law because there's no acceleration. So we know that we have the spring is wanting to pull up and return to its equilibrium position. Okay, so that's wanting to pull up and it's positive, but we also have the mass pulling the spring down, keeping it away from its equilibrium position. Okay, so that's why it's negative, because it's pulling down. These things have to cancel each other out. So if we look at our Newton's first law equation here, we know that the force of the spring and the force due to gravity on the mass, they have to be equal and opposite. So here I have them set equal to each other. Okay, so the mass is responsible for a certain amount of displacement, right, which we've talked about. So we've got delta S. Now, and we're just going to use delta S in the generic sense where it could be delta X, delta Y, no one cares. So this displacement, we can actually update this here if we want to, delta S, which is a change in L in our case. So the mass is responsible for this, for pulling this down. So if we were to increase the mass, we would also increase the displacement. If we hang more mass on there, that spring's going to stretch more and more. So let's use that idea to actually discover Hooke's law here. So we'll essentially do this experiment, step through it, and it'll actually help us build Hooke's law from scratch. All right, so you can imagine over here, just like I said on the last slide, if we keep increasing this mass, we keep pulling the spring a little bit more and a little bit more. Okay, now if we do this several times and actually plot this out, we actually determine something really interesting. So let's say I'll do green for increasing mass. So let's say we go from a mass of 1 Newton, or a mass supplying 1 Newton of force. Let's say we add on another half Newton, 0.5 newtons, okay? So you'll see that we have a change at delta F, okay? We have a change in our force. Well, that change in force, since we're increasing it, that's going to correspond to a change in our position, our stretchiness of the spring. Okay, so if we keep doing that, and we can do that, you know, several more times, we maybe add some more mass. If we do that and plot the amount of mass we add to the spring and then how much the spring is displaced, it turns out this is actually a linear relationship. And this is actually something you just got to do and actually plot these points, and you can see experimentally that you do have this relationship here. So since we know that it's a straight line, it's linear, let's actually see what we can build here. Okay, so we know that on the y-axis we have the force of the mass. Okay, so on the y-axis we have the mass. But you'll remember on the previous slide that the weight of the mass and the force of the spring pulling up, those are equal and opposite, okay? So I've got that included here. Okay, those are equal and opposite. That corresponds to our y, and our y equals mx plus b linear relationship. Because remember, the y equals mx plus b linear relationship. Now we know that the y is the force from the spring. Well, now we know what the x is, because here on our x-axis, let's see, I'm going to label this y. We know on our x-axis, I'm going to jump down here and label it blue. On our x-axis, that that's the displacement. That's how far away we are from equilibrium. Okay. So that's here. Well, this plot, if there's no mass, there's no displacement. So we know that b has to equal 0. Okay. No mass, no displacement. So we know that b is 0. The only thing left that's interesting, well, I'll circle this here to show that our y-intercept is 0, y naught, which is also b, is 0. Now, the interesting piece here is our slope, okay? We do have a slope. If we think about the units on slope is always rise over run. Okay, so the rise, that'll be the y-axis. Okay, so let's see, slope. Ooh, I want to use a different color for this. Let's see what I have. Black. Okay, so slope is rise over run. So the rise is going to be in newtons, but our run, the horizontal part, is going to be in meters. So we know that the units of our slope is units per meter. Okay, well, it turns out that this thing, this slope, is actually the spring constant. And it does indeed have units of newtons per meter. Okay, so this slope, this value here, that essentially tells us the proportionality constant, right? Okay, or it tells us how proportional the spring is in supplying a force to how much has been stretched. So I think I'll just read the sentence so I can state it succinctly. So the restoring force provided by the spring is proportional to the amount the spring is displaced. Okay, so all of this is K, and this is just our slope. That's the relationship between the two. And we call that the spring constant. Okay, so do note that the force does not depend on the spring's equilibrium length. So it doesn't matter how long the spring is. The spring could be 10 feet long or it could be 10 centimeters long. No one cares. The force does depend on the displacement from equilibrium. Okay, so not how long the spring is, but how much has been stretched or compressed. That's what matters here. So if K, remember that's our slope, if K, the slope is large, the spring is stiff and it is hard to stretch, okay? Which means that it takes a lot of newtons to get a meter stretch out of it, okay? Lots of newtons per meter, okay? So that means you've got to put in a lot of force to get a change in distance or a change in position out of that spring. Now, if K is small, then the spring is soft and it's super easy to stretch, okay? So the idea is when we think about the units of K and that relationship, small newtons or small force, big change in the length of the spring. It's going to be a little force is going to make it super compressed or super stretched. Okay, so that's all K is telling us is how much effort it's going to take to change the length of the spring. At the same time, K tells us how much force the spring can give us back in return. Okay, so do remember that the direction of the spring force is always opposite the direction of displacement. Remember when we pushed a spring in, when we compressed it, it wanted to act opposite of that to go back to equilibrium. When we took the spring and stretched it, it wanted to act opposite of that to go back to equilibrium. Okay, so a good grief, a stretched spring in the positive direction wants to return to equilibrium, which would be in the negative direction. A compressed spring in the negative direction, so we're making this length shorter. It wants to return to the equilibrium by getting longer, by going back in the positive direction. Now we know we have this slope, the K, we know we have the X, so we know we have this Y equals mx situation going on here because there's a linear relationship. What we can do is we can add a negative sign, and that takes care of our restoring force. Adding that negative sign in there is the final piece of Hooke's law that says, okay, these springs are going to act opposite to what we're doing to it. So we need to include that negative in our mathematics to reflect that. Okay, so this right here, this force equals negative K delta S, this is Hooke's law. And basically just tells you the force that a compressed or stretched spring provides. And at the same time, it tells us how much force we would have to apply to compress or stretch a specific spring. Okay, so down here, I've included this figure again, just to remind you that, it's equal to the direction of displacement, and the force will always oppose the thing you're doing to the spring. So let's quickly think about this quick problem here. So we have the graph showing force versus displacement for 3 springs. So it wants us to rank in order from largest to smallest the spring constants for A, B, and C. Okay. So these 3 plots are actually the same plots from the previous slide. So we have our displacement down here, delta S, and we have the force being used to actually make that displacement happen. So you'll notice that A, I don't think I want to write big, I think I want to write large K. So slope A here, this first one, actually it's got a big slope. So this has to be a large K. Okay, so we know we're ranking from smallest to largest. A's got to come first. Well, clearly this is like a medium K because it's got a medium slope, which means C down here has to be a low spring constant because it's got a very shallow slope. The slope is not steep at all. So let's think about this. Okay, so if we apply let's look at C here. This is one with the small spring constant. So remember, it's going to be a soft spring. So if we apply, look at this, if we apply a huge big stretch here, okay, so if we take a spring C here and we just stretch the crap out of it, look at what that's given us. So even if we just stretch the crap out of it, we're getting a really small return here. Look at how much bigger the delta S is than the delta F. So you can see that this is a soft spring because big stretches or big compressions really just give us a little bit of a force. Whereas, let's see. Whereas, let's look at this larger one. Okay, so if we apply just a little bit of a displacement, look at how big of a force we get. So it's somewhat poorly drawn. I guess this should be a little bit higher. There we go. But you know, when you compare that over here to just a little change in force from a big displacement, you see that this is actually a stiff spring, and this is actually a soft spring. Right, so hopefully that makes sense. Stiff spring, soft spring, large K, small k. That's just a spring constant to let you know essentially how resistive to changes the spring is. Okay, so let's look at elastic potential energy. Okay, so we have a spring force, which is a variable. Okay, so the force is 0 if there's no displacement, and it steadily increases as the string compresses, increases. Yep. So we know that. Let's see. Yeah. Stretch increases, stretching, compressing. Yep. Okay. So let's apply Newton's second law to this, just like we did in the last lecture. Okay. So given the fact that if we have the forces added up on the spring, okay, so we have Newton's second law. We know it equals m times acceleration, which we can rewrite as dv dt. Now, the force, Hooke's law, we know we can represent this force, okay? So Newton's second law situation, okay, we're summing up the forces, but we know the force on the spring is going to be negative k delta s, okay? So here we sum the forces. The only force acting is the spring force. We can rewrite that as the delta s, or the s minus, or the difference in final minus initial in equilibrium. Now I'm interested in this piece here and this piece here. Okay, we know they're set equal to each other. So I'm just going to pull those two pieces out and set them equal to each other. Okay, now I'm going to use the chain rule again. Okay, so the chain rule is going to apply to this first term here. So I'm going to rewrite that dv dt. Okay, I'm going to use my trick where I multiply by 1, which is essentially ds over ds. I can do that, but if I multiply by 1, I don't change anything. So it's a totally valid maneuver. Right, so when I multiply by 1, I can rearrange the denominator, and it turns out I get my velocity times how my velocity changes with respect to a position. Now I can take that and plug it back in to my original equation that I'm interested in. Okay, so here's my substitution. And of course, this is just equal to negative k delta s, right? Nothing's really changed. We've just written something differently. But what I can do is I can actually multiply that ds over. You know, since these functions, these derivatives are nice and well behaved, we can do this. And then from here, you'll notice this is where this line comes in. I can integrate this. So everything I have here in green, let me change this. So everything I have in green comes from this first piece. I can integrate it easily. It's done all in one line. You remember this from the previous lecture. We know that this is actually just the final kinetic energy minus the initial kinetic energy, because this is just the mv/dv. We're just integrating momentum essentially. But now you'll notice I haven't done this integral here yet on the right-hand side. Okay, so this one, is still a bit of a question mark. I have not done this integral yet, and the reason is we need to use a u substitution to do it. Okay, so it's going to get a little fancy here. Okay, so let's use this u sub. So we're going to say that u equals essentially delta s. Okay, so instead of just trying to distribute the ds and everything, let's be fancy. Okay, so u equals delta s, and then when I calculate my du, my du, it just becomes ds, right? I'm sure y'all remember this from the end of Calc 1, beginning of Calc 2. Either way, we can actually do this really quick if need be. So the whole idea is essentially you just pick a complex piece inside of your integral and substitute something easier. So I'm going to say u equals the stuff inside. Okay, well, I need to take the derivative of u. So that's going to be du ds. Well, the derivative of s is just 1, and then se, that's a constant. So the derivative of that becomes 0, and now I'm just left with du ds equals 1. Okay, well, I can actually multiply the ds over, and that's how I get this statement, du equals ds. Now, the next thing I need to do is change my limits because I'm going to go from a ds space to a du space, okay? So my new limits here are going to be, instead of just integrating from si to sf, I need to integrate to from ui to uf. And it turns out when we plug these in, ui is just the change, the initial change, si, and then so the initial length of the spring, and then my final new limit is the final length of the spring. So it could have went from stretched to compressed or compressed to stretched. Okay, so I can make these substitutions here. So you can see my s minus se, well, that just becomes u. My limits of integration change. So instead of si, I get delta si. Instead of sf, I get delta sf. Okay, now all I have to do now is just integrate u and then evaluate with these new limits. Okay, well, you remember from by now that the integral of u to u would just be 1/2 u squared. Okay, I've got that. Now I just have to evaluate my limits of integration. Okay, so it's going to be my final piece plugged in minus my initial piece plugged in. All right, and here's what we're left with. So I'm bringing this down. Remember, the left-hand side was easy, but we had to do some tricks here to integrate the right-hand side. But what happens out of all of this is essentially we have something similar to the last lecture, where we have the final kinetic energy minus the initial kinetic energy. And then we have these two new terms. They look like kinetic energy, but notice this has to do with position. Okay, so we have a 1/2 k delta s squared. All right, so let's go ahead and move my before stuff and my final stuff around. Okay, so we'll get the before and the after together. So I have my initial pieces here. I have a kinetic energy, and then I have this new thing. Then I have a final kinetic energy and a new thing. So now the question is, what is this new thing? And we're defining this as the elastic potential energy because it still deals with the position. Now it's just a horizontal position. Okay, so if you look here, you'll see that we have initial and final kinetic energies, and we also have initial and final potential energies. And notice that these energies are conserved because what you start with equals what you end with once again. So these energies are still being transferred one to another. Okay, so let's sum up potential energy really quick. Then we'll do an example and then we'll call it, okay? So an object moving on a spring obeys this equation. So you can think about an object maybe like this on a spring, and maybe it's been stretched from equilibrium by some amount. It's a delta S. All right. So when you have the situation, notice we do have spring potential energy. And then as this thing moves, because the spring's going to want to move, this ball or this mass is going to have kinetic energy as well. So whatever this system starts with still has to equal whatever this system ends with. So mechanical energy is conserved if the object is moving without friction on an ideal spring. Okay, so essentially that means a massless spring where you're not losing any energy for some reason from the spring. So in kind of this ideal model scenario, mechanical energy is conserved. So if the spring is moving vertically, now this is key. So an object on a spring can move vertically. That means the mechanical energy is going to have kinetic energy. It's going to have gravitational potential energy. So grav potential energy. And then it's also going to have spring potential energy. So the idea here is that we could have 30 different types of energy, but the total mechanical energy is just the sum of all of those energies. So this is just the sum of all energy. And if you're not losing any of this through like friction or something, then the total energy's got to stay the same no matter how these energies are transformed one to the other, because you can imagine putting something on a spring, the spring raises it vertically. Well, some of that spring potential energy is converted into gravitational potential energy, but the total is still the same. So let's put this these ideas into motion here, so to speak, and actually solve an example problem. So we have a spring with constant, we have a spring with a spring constant of 2,000 newtons per meter, okay, and it's sandwiched between a 1 kilogram block and a 2 kilogram block on a frictionless table. Okay, we've got that set up drawn here in the before. These blocks are pushed together to compress the spring by 10 centimeters. Okay, so we're going to have a restoring force. Okay, and then it's released after it's been compressed. So what are the velocities of the blocks as they fly apart? Okay, so that's what we're after. We want both velocities, the velocity of block 1 and block 2. So we have a two unknown situation, which means we're going to need two equations. So assume, okay, the ideal spring obeys Hooke's law. There's no friction. The mechanical energy is conserved. Okay, so it sounds like it's going to be easy when we modeled this. We're just going to use the classic sort of idealized model. You know, there's a lot of situations where this will work in the real world. But of course, in the real world, it's not exact, but it's still a good model. So in addition, the blocks and spring form an isolated system, so their total momentum is conserved. So that means our system is the two blocks and the spring put together. So here's our pictorial before and after. Okay, so let's find, like the problem says, the final velocities of both. Okay, so again, the system is defined as both masses and the spring. There's no friction, so that means there's some conservation going on. Okay, so we're finding two velocities, so we do need two equations. So that means we actually have to use two concepts here. Okay, so in this system we have momentum and energy are conserved. So we have momentum equations and energy equations. So there's our two equations that we can solve for two unknowns with. Okay, so let's look at momentum first. So remember, capital P means total momentum. So our total initial momentum, big P, I, is going to be the initial momentum of the first block plus the initial momentum of the second block. That momentum, the initial momentum, has to equal the final momentum, okay? Which of course is just the final momentum of the first and second block. That's easy to set up. Okay, now let's think about, we've done the momentum equation, let's think about the energy equation. So we have two different types of energy here. We have kinetic energy, because these blocks are going to fly apart. We also have potential energy from the spring. Okay, so we have no gravitational potential energy, but we do have spring potential energy. Okay, so here's our initial kinetic energy and initial potential energy. Okay, well, we can write these out. So we have the initial kinetic energy of the first block. Oh, little typo, these should be 2. So then we have the initial kinetic energy of the second block. Same thing here. Okay, so now we have this initial potential energy of the spring. And then these two kinetic energies plus this initial potential energy, whatever we start with, we have to end with. Okay, so over here we have, oops, I'm going to do this in orange. So over here we have our final values. This should be 2's. Okay, so we have our 2 kinetic energies and then our final potential energy from the spring. So obviously this bottom equation is like big and gross and hairy, but some of these things are going to be 0 and it will get much easier. Okay, so let's think about the momentum approach first. So we have initial equals final, same equations from the previous slide. Notice here in red, these are 0, because remember, these things are compressed and they're being held there, so their initial momentum are 0. Okay, so this is gone, and it turns out, since the initial momentum is 0, it's just the final stuff added together equals 0. So this is easy to solve for. So what I'm going to do is essentially just solve for one of the velocities. You can see here I've solved for the final velocity of the first block. You can do the quick algebra, and it's really just the ratio of the masses times the velocity of the second block. Okay, so looks like we're good to go. We've solved for the final velocity of one of the blocks. That's what we wanted. But we can't get a number yet because the final velocity of the first block depends on the final velocity of the second block, and we don't know what the second block's velocity is. So let's move to the energy setup. Okay, so we know that the mechanical energy in the before and after is conserved. Okay, so let's write this out. So we have the initial kinetic energy of both blocks. They're not moving. Remember, they're smashed together and they're being held there. Both of these terms just go away. The only thing in the before situation is that spring potential energy getting ready to push those blocks apart. Now let's think about the final, or the after picture. Okay, so we know that both blocks are obviously moving. Okay, so we've got block 1, block 2, they both have kinetic energy. Well, the springs return to its equilibrium position in the final picture. So the delta x final, that's just 0 meters. It's returned its final length. Let's see if we can write it out here. Let's do delta x equals, okay, its final position now is its equilibrium position, but then it started in its equilibrium position, so that's just 0. And that's why this term here goes away. It's returned to its equilibrium state and it's no longer supplying any energy. Okay? Now, I've got an equation over here where I've solved for V1. So let's solve for V2 and get that final velocity. That's why I have it here in green. Okay, well, I've done some simplifications. Every term has a 1/2, so those 1/2s can go away. And now we're left with this statement here. So it's going to get a little gross, but that's totally fine. We can do it. Okay, so using the definition of V1 from momentum, we can actually solve for V2. So notice we have this thing in our way, but we want to get this thing. So what I'm going to do is take my definition of V1 and just use it. I mean, we know they're related, so we can actually take these two equations and put them into each other any way we want to. Obviously, some ways will be more helpful than others, but as long as you're consistent with which direction you're plugging these in, you're good to go. Okay, so I'm going to take essentially my V1 from the momentum aspect of this problem, and then just plug it in into the equation right here. Okay, well, I can do some simplification, and I won't bore you with the algebra. That can be something that you can do. But essentially, all I've done is I've combined these two terms, right, to just give me something a little more elegant. Okay, so I'm going to take, I'm going to take this piece, and I know it equals this piece. I've just done some algebra in between since I've plugged in my V1 final, and now I'm just going to solve for V2. Okay, so I get this kind of gross equation, but you know, it's just some algebra. It's not terrible. So this is my calculation for my final velocity of the second block. Okay, so I can start with that equation, right? I know everything in there. I know the displacement, I know the spring constant, I know the masses. So now I'm good to go. I can plug in numbers and actually get a value out. So when you do that, it turns out the final velocity of the second block is 1.83 meters per second. Now we can return to our original momentum equation. Remember earlier I said we had no idea what this value is. It turns out now we do. We just solved for it. Okay? So I can plug in those values. I know my masses. I just solved what the final velocity of the second block is, and it turns out my final velocity of the first block is negative 3.66 meters per second. Now let's do a quick sanity check. We know that to the right is the positive x direction, which means to the left is the negative x direction. Do our signs make sense? Let's see. So this is positive. This one's negative. So yeah, it looks like at least sign-wise, our answers line up. So that was a simple example of how you can use energy and momentum, two equations, two unknowns, to actually solve for multiple velocities or multiple unknowns in these momentum and energy problems. So let's look at a quick summary and then we'll end here. So restoring forces seek to bring the system back to equilibrium. Okay, and we can calculate some of these restoring forces from springs with Hooke's law, which is just negative k delta s. Okay, now that k is a spring constant. Okay, and we know that a large k value is a stiff spring. It's hard to push or pull apart. And then a small k value is a soft spring, so like a slinky. The elastic potential energy of a spring, or maybe like a spring-like bond in a molecule, that's just 1/2 k delta s squared. And then, of course, the idea of mechanical energy being conserved, we talked about that last lecture, but we've added an extra type of energy that we can throw into the mix. So now we know that the kinetic energy, the gravitational potential energy, and the spring potential energy, if we have all three in a problem, the amount of energy we start with has to equal the amount of energy we end with. All right, so if you have any questions, I know that I did this problem fairly quickly. If you have any questions about the algebra, maybe there's a tricky step in there, or maybe something you're not seeing, please let me know. I do want to just say that the overall idea is essentially to just use the fact that momentum is conserved, one equation, energy is conserved, another equation. So we have two equations allowing us to solve for two unknowns in a problem. If we have an elastic collision where things bounce apart and we have two things in the beginning and two things in the end, this idea here where the energy and momentum are both used, this is crucial. So do take a few minutes to make sure you understand some of the tricks in the algebra in this problem and make sure you get the whole idea of the two equations, two unknowns.